pretty exciting to be here. So we hope that you can take some of these approaches and lessons that we learned and integrate them into your own systems. You may find some of this content familiar, and that's probably because the data problems that DraftKings have are felt widely across the industry. So we're simply here to share what has worked for us, both technically and organizationally, and that hopefully can help you too. So for a little overview, first we'll cover a bit about us and what we do. Then we'll go over what motivated us to push the platform forward, some iterations toward this aim. We'll cover some of our successes and failures, and finally what lies ahead of us to try out for this year. So my co-speaker Tom and I worked on this project together last year. It was the first initiative I led after joining the company, and I'm really thankful for his practicality, ingenuity, and focus on simplicity that were all key to the project's success. So for those that don't know, what is DraftKings all about? So if you're not into sports or betting markets, the three pillars of our product offerings are Sportsbook, where folks place bets on which teams win or lose games, or how many points players will score. This is where most of the revenue comes from and where most of the platform traffic originates. The key characteristics of the Sportsbook data is that it's highly variable, can often spike in volume many multiples within minutes, and this happens often around key events like touchdowns or turnovers in a tight game. So next up is iGaming, which is our online casino. Here folks can play hundreds of games of chance, from live dealer poker to slots. The traffic coming from iGaming is generally less spiky, but since it's not related to game times that are known beforehand, it can still be somewhat unpredictable. Finally, our original flagship product, Daily Fantasy, where folks can create their own teams and compete with their friends. Due to this being a less real-time product, it generally does not generate a huge amount of data volume, so it doesn't factor as much into our scaling equation. When it comes to the platform team, I would say that we resemble most companies our size. We have different squads that make up our data platform that focus on infrastructure tooling, data ingestion from our application databases, governance of protected player and gaming information, and overall developer experience and administration of our data lakehouse. For our Snowflake squad in particular, we handle resource provisioning, working with stakeholders to make sure they are able to hit their SLAs consistently. That means both front of house, where we guide them to improve their workloads directly, and back of house scaling work to make sure that we are balancing performance and costs effectively. We also create and improve the tooling for different workflows that we support to meet the needs of our different users. Data engineers, scientists, and analysts, they all have their unique use cases, and that needs to be worked together in a cohesive environment, so we help bridge those different roles. Within an organization as big as ours, making sure nothing slips through the cracks can be difficult, and so we also handle the core alerting and monitoring across our handful of Snowflake accounts. So with that all out of the way, we can get to the real reason why you're here. So before we dive into the technicals, I want to set the stage with what it was like before we had autoscaling. So I want to emphasize that between college ball and NFL, weekends have a lot of games played, which meant that every weekend during the season was kind of a soft on-call for the team. Now, I joined DraftKings in between football seasons, so I never experienced how hectic it was firsthand, but I did collect battle stories from those that came before me, and here's how it went in my imagination. So it's 8:45 p.m. on a Sunday, and two back-to-back upset touchdowns caused a huge surge of activity on the platform. Jobs are taking way longer than they're supposed to, so latency keeps increasing. Our on-call team member here, he scales up, but the back pressure keeps building. The jobs are still underway, so he'll have to wait until they finish before they can make use of that extra compute. Hopefully the scale-up will take care of everything and we'll be back to normal in a bit. All right, it's 10:32 now, and he just got like the fourth ping from senior leadership. They're justifiably frustrated because their dashboards are now 2 hours behind. He scaled up a while ago, but it's still not catching up. So we need to scale again to be faster than incoming data so it can chew through the backlog and get us caught up. So hopefully we're round two. This will sure do the trick. So now it's 12:41 a.m. and the scaling did work, and the games are over, so bet placement volume has dried up. He thinks, okay, the worst is over, I can scale down for now. Then he remembers we still have to settle all those bets that were placed so we can actually pay users out. Settlement is kind of like clearing a check or a bank transfer. We need to confirm that everything is correct before funds are released. That doesn't happen until maybe 1 a.m., and so he'll just have to stay up waiting until that kicks off. The coffee doesn't seem to be working anymore, and I guess judging by the image, neither did printing out a bunch of paper. So let's check back in on our guy a little bit later and see if he's still holding up. It's now 1:26 a.m. Maybe the staying up part didn't go so well. All bets have been settled, traffic has fallen off a cliff, and most users are now asleep, just like our guy here. Better make sure to wake up, buddy, because we need to scale the warehouses down or we're gonna run up the bill doing a whole lot of nothing. So now that we have a good image of the before times, let's see how our guy here did with his autoscaler this recent season. Okay, well, check this out. It's 7:14 on a Sunday again, but this time we're at home with the family. We got a nice sunset, mom's spaghetti, little Tommy sneaking some green beans to Rufus over there under the table. Instead of a hectic office, we're pretty much in a Norman Rockwell painting. But the night's just getting started, so I'm sure when the bets really start flowing, we'll see our guy here get paged in. All right, well, it's 9:32, and I guess instead of watching some graphs about the back-to-back upset touchdown traffic spike, he actually got to watch it in the game. Well, that's certainly an improvement. Well, let's let him have his moment for now, because like we saw earlier, it's gonna be a long night waiting up for that settlement to kick off. So we'll check back in one more time and see if he's got any papers printed out. All right, well, guess not. It's 1:26 a.m., our guy here's sleeping like a baby. I guess he's really confident in that autoscaler. So, I mean, now I'm curious to see how he pulled this off. So you're probably thinking, hey, it's the cloud. It's a virtual warehouse. You can just scale up and down whenever. It's so simple. And that is true, but doing so without just spending 2 to 4 times the money is the hard part. It's so hard, in fact, that here at Summit, you can check out the booths of companies whose entire business model is to help customers not overspend. So before I go into what approach we took for this past season, first I'll go over how we used to scale for NFL. You can see how this can get out of hand pretty quickly without a very responsive scaling policy. So here's the overall system design in the simplest of forms. We have some application databases that most of our data originates from. There's hundreds of these things since DraftKings has lots of services that power lots of products that are located separately in lots of jurisdictions. We use AWS DMS tasks to replicate the data from the bin logs of the databases into S3 and then Snowpipes, which land the data each minute or so into the raw log tables. Each 2 to 5 minutes, we take this new data and we merge it into the resolved data that contains the newest up-to-date state. Pretty simple, you've probably seen this before. 2 seasons ago, work was done to identify the critical workloads of the data replication merge tasks and ETL jobs and separate that work out into their own warehouses. So this was definitely a positive step forward to limit the amount of contention around critical workloads. The less you have running on a warehouse, the more consistent the runtimes can be. During hours where NFL games were common, we had an airflow task scale up and down the warehouses based on some primitive data latency checks. This worked well as a first approach, but had a few significant drawbacks. It only supported a fixed SLA with no differentiation between what's needed for game times and non-game times. It was only active during certain days and around hours that generally had NFL games, so there's no 24/7 scaling at all. It only supported scaling up one fixed level. It scaled on downstream end-of-the-line analytics table latency, which meant that the latency signal lagged the upstream merge tasks volume growth by about 30 to 40 minutes. And all warehouses were scaled up as a group and down as a group on the total end-to-end latency instead of scaling individually based on their portion of the pipeline's latency. So here we have a visual on how it takes a while for the data throughput increases to propagate down the pipeline. The vertical size of the box indicates how much data is processing. The horizontal size indicates how long it took to run. And we can see that by the time the gold bar has increased in its runtime enough to trigger a scale up, the bronze bar has already doubled in its data size since the batch that made its way to the gold step. If we were to scale everything up based on the increase to the gold section over baseline, we would be significantly underestimating how much we need to scale the upstream portion. So this was the primary issue with scaling based on the downstream signals. Now that we want to shift our scaling operation left, upstream, let's zoom in on that bronze section and see what the behavior looks like there. So the primary issue at hand is that latency cascades, which means that long job runtimes cause even longer job runtimes. So this is due to the combination of batch processing and fixed execution schedules. We were merging in change data capture logs in 5-minute windows only on every 5th minute. So you can see here at the bottom that we have an incoming data rate where the color gets darker when the rate increases. One thing to keep in mind is that when a task kicks off, it's processing all of the data that came into the Snowpipe and stream prior to it kicking off. So the data rate starts increasing at the 5-minute mark, but it doesn't really take effect until the task kicks off at the 10-minute mark. We can see that prior to the third task, it only takes 3 minutes or so to execute, so we are well within the naive SLA determined by our execution frequency. Once the data rate increases, the task now has to process much more data, but the warehouse size has not been adjusted, so it takes much longer. Because we are using Snowflake tasks and we have concurrent executions disabled, Snowflake simply skips executing a new task until not only the previous task is done, but until it hits the next scheduled execution. So that would be the 10-minute mark. This means that the task that took 7 minutes doesn't cause the next task to process 7 minutes of data, but 10. So now that we need to process 10 minutes of data, it takes the next task 14 minutes to finish, which then causes the next task to take even longer, and so on. So how do we avoid this issue? Here's a similar graph, but now we have the incoming data rate in red and the processing rate in green. The processing rate here is affected by warehouse scaling events. Here the strategy is to scale up whenever our task misses its SLA of 5 minutes and to scale down whenever it finishes executing in under 2 minutes. So the first 3 task executions look exactly the same as our previous graph. But now when we exceed that 5-minute SLA here, we scale the warehouse up immediately. Now even though we scale it at the 5-minute mark, we have to wait until the next task kicks off to actually use that scale. So the processing rate doesn't increase until the next task kicks off. So even though just like before, we were trying to process 10 minutes of data of this increased data rate, because we had scaled up, we only take another 7 minutes to execute. So this does mean that though we need to scale up again, because we need to be able to process this 10 minutes of data in less than 5 to get back to real time. And we still haven't gotten there yet. So now that we're scaled up again, we are finally processing 10 minutes of data in under 5 minutes, and we are once again hitting our SLAs. But this means that the next task will only need to process 5 minutes of data, which is great. Because we're scaled up so high though, it crushes it in 1.5 minutes, which is way faster than we need to. So we scale down a level. So this brings us back to our steady state, 3-minute task executions, and the scaling cycle, it's finally over. So when we set out to tackle the size-based scaling issues, we weren't completely starting from scratch. We had previously made a service for concurrency-based scaling of multi-cluster warehouses. We know Snowflake offers that functionality natively, but we wanted to be able to have more control over when that warehouse added more clusters. We have some ad hoc warehouses that people run queries on for work that's not time sensitive. We want to make sure that we are pretty much always queued so that we can ensure cost efficiency. Snowflake's native scaling is more biased towards maintaining performance, so generally we would scale up more aggressively than we wanted for those warehouses. So this service is super simple. First, we gather the stats in the warehouse queue and the cluster count using an AWS Lambda. Then we send it to an SNS topic. We mostly did this so that we could inject other scaling signals into the process if we wanted, to extend this with manual overrides or anything else. Then another Lambda will read from that topic, and for each warehouse, it will check its configuration to see if the current queue size is over its threshold, and if we need to scale up. That's about it. The simpler the system, the more reliable it is, and from the beginning, we never had any issues with this approach for what it did. So after all that, you're probably thinking, okay, maybe it's not quite that easy, but it's still pretty simple to scale up and down on SLAs, right? And that's true. It's generally a simple thing to do. But as always, once you dive into it, it gets a little more complicated. So with that said, I'll hand it over to Tom to go over all the ins and outs of what we actually built.
All right. So, once we came to the conclusion before the NFL season last year that we wanted to start building out this new scaler, we had a couple considerations to start with. First, how were we going to determine what to scale on, right? So there was 2 initial approaches. We could try and predictively scale. So we could try and get the warehouse size to the correct size before those tasks started executing, which led us to look at incoming data volume and trying to determine whether or not the warehouse was correctly sized for the potential incoming volume for the next task run. And this is really nice, right? It allows us to hopefully keep the SLA constant and always be at the right size before a job kicks off and never have to worry about catching up because we're always kind of ahead of time. The other way of going about trying to scale is doing it reactively. So reactively is obviously super straightforward. We have an SLA set, If we look at that set SLA and we look at our previous execution time, we know whether or not we're within that SLA bound. If we're not, we can scale up. If we're going too fast, we can scale down. So first, looking at some of the kind of questions we had around predictively scaling and what that would look like if we were to find those predictive measures. We wanted to make sure that we could actually actively get the metadata for all of the incoming data, get that data volume, and make sure that it is actually indicative of the runtime of the task that volume is contributing to. And then so we also want to make sure that that work is, or that kind of scaling metric or signal is generalizable for all of the workloads, right? So if we're looking at one table or potentially one database that's coming in, is that indicative of the kind of runtimes we're going to see across warehouses, across workloads, across business units? And then consistency, right? So if we're looking at this one metric, this one signal of incoming data volume, is that always going to be correctly predictive of the scale we want to be at? And can we rely on that for real-time scaling? And so after doing some research, we kind of came to the conclusion that unfortunately this is not the case for a lot of the answers that we were hoping for. Right, at least for the incoming data volume coming from our pipes, we couldn't find a signal or source that could both reliably give us the latency and resolution that we needed to be scaling this frequently. So the Snowflake pipe usage history view isn't quite high enough resolution or low latency enough for us to be able to scale as frequently as we were looking to, which was on 1-minute cadences. The other option for that scaling signal was looking directly into our S3 buckets, looking at the metadata and the size of the files coming in, and seeing if we could scale off that. But none of that was immediately available or kind of out of the box. Would require some custom work on our part, and would also just require like a lot of another service / spending compute on actively analyzing all that metadata and trying to get it back to the service in time for us to actually action those signals. And then the question of generalizability, right? We didn't find any good correlation across these signals coming in and the actual work and the time is taking those tasks to run. A lot of our workloads and merge tasks can have multiple different types of joins or ETLs going on with them. So they become very nonlinear with kind of the base level data volume that's coming in. So we can't consistently say that across all these workloads, increased volume in one area is going to necessarily, linearly correlate to this kind of increase in runtime over here. And then consistency, right? So we can't, the ratio of updates to inserts in some of these tables that we're trying to scale on isn't always, for that incoming volume, it's not always predictable, right? We can't know that if we're going to have 1,000 records coming in, what percentage of those are going to be inserts or updates, and the associated amount of time is going to take the task to run either a certain percentage of inserts or updates. So it wasn't really consistent. We couldn't say that just this much incoming volume is every time going to indicate a certain amount of increase in SLA or runtime. So then next we had to look into how we might try to find a reactive scaling signal. And this is still a little bit more straightforward, right? A little bit simpler. How do we define SLA? It's easy. We know what our tasks are, how long we expect them to run in, and how long we need them to complete by, so that the next part of our pipeline or next downstream system has data on time, right? And luckily for us, Snowflake gives us all those task execution times pretty much for free. We're already making some Snowflake metadata calls, so we don't have to do anything or build anything custom there. Generalizability. So how do we coordinate scaling across the different warehouses? And how do we know when to scale up and scale down across warehouses? This is also pretty easy too, because we know the work that's on each warehouse, so we know the SLA to tie that to. So it's easy to tie what's the work running there, and make sure it's always generalizable to the execution times. And then, is reactivity enough, right? So Hank just walked through all of the potential issues we've had with cascading failures, or cascading latency. And so if we're having cascading latency and we're reactively scaling, are we able to still scale fast enough that we don't already miss the boat, right? We don't let the back pressure get so large that we can't get ahead of it with the next scaling signal. Right? So some of the answers to these questions, right? Like the SLA, right? It's already tied to the execution time and the task, and we by controlling the next executions times, we know what to target. If we have a job kicking off every 2 minutes, we want to make sure that it's running in 2 minutes or less, right? So the finding that SLA is pretty easy to work with the business partners or the stakeholders who are dependent on these tasks to make sure we have that SLA. But the generalizability, kind of already talked through it, but we have these tasks that we know are indicative are indicative of the entire state of the warehouse. So there are a few tasks that are going to be contributing to the, or kind of, we call, they're indicative of the entire workload on the warehouse. So if we know that this is running or over SLA or under SLA, everything else should be scaled according to that. So we have these kind of like bellwether tasks we can peg to and scale based off those. And then is reactivity enough? We did some additional work here to increase the frequency on some of these tasks we're running, so that we never let the back pressure build too much. And because we're able to scale up multiple times during a single task execution, we can still guarantee that even though the one task might reach SLA, that the next one will be properly scaled and properly sized to make sure that we don't have another SLA breach after that. And then just some quick final considerations, right? A lot of the work here wasn't just pure technical work and going in and scaling some of these warehouses and trying to build out this service. There's a lot of work to be done with the rest of the business. So working with domain teams and business stakeholders to kind of find these variable SLAs, making sure that we know how long we want stuff to run, and at what time we need to be held to those SLAs. Stakeholder self-service. So this is pretty big for us, because as a platform team, we don't want to be in the situation of having to know all of the game times, having to know when specific the business specifically wants to scale for something or some event. And so allowing other teams to be able to insert scaling events or scaling time periods into the service is huge for us. Alerting, right? So if we're just going to let this service scale all of our warehouses for us during some of our most critical times of the year without us having any manual intervention, we need to know what's going on, what it's doing, when it's doing it, where we are within our SLAs or within the game context. So building out alerting was huge. And we need to make sure that this works not just for NFL Sundays, not just for college football Saturdays, but it works for every day of the week, every sport that we cater to, and even custom events that we might not be able to foresee right now. Yep. So getting past all that, we can just kind of start talking about how we actually built this out, and kind of just go through the service that as it stands today. Yep. And Hank showed this earlier, but so this is just kind of like another higher level view, just kind of how we bootstrap the service onto the existing kind of pipelines. And we'll show a little bit more, go into some more detail on this, but right, so the service sits on top of our warehouses. It uses per warehouse config files so that to know how to scale each warehouse, and then it pulls metadata from both our job coordinator, Airflow, and our Snowflake tasks to know the current execution times and the current executions, and all of the infrastructure looks the same sitting in AWS running on Lambda. But yeah, so this is the new and updated version of the autoscaler. So just doing a quick run through of how the process works. Right, the first thing we're going to do now is reach out to Airflow, our job coordinator, and get all of our tasks or Airflow jobs that we're tracking and we're scaling based off of. And we're going to see that DAG history, and we're going to pull in all the metadata around those executions, and we're going to provide that to our status Lambda. Our status Lambda is also going to be pulling all the task latencies for our tracked tasks from Snowflake. It's also then is going to be pulling from our SLA sizing tier. So this is how we know what the current SLA is and what the current level of priority we're in is. I'll go into this a bit later, but this tells us whether or not this is a business critical moment and we need to be scaling higher, or if this is a more relaxed downtime where SLA is less of a priority. And from there, we can also have custom events that the business is able to inject in there so they can have custom scaling schedules, even for non-tracked game schedules. But all that is then pushed to our same SNS for alerting to the next Lambda, which is actually going to be doing the right-sizing actions. It's going to take in that the metadata around the warehouses and the tasks. It's going to determine if it's a good time to scale up or down, in or out. It's going to execute that, log that into Snowflake, and then all that's going to be visible through some of our alerting dashboards after that. So this is a snapshot of what the config file looks like for any given warehouse. So we'll start off with the warehouse name at the top. And then so that first 0 indicator there is going to be the priority level. So a 0 would indicate not priority level for us. So this is pretty much downtime. This is normal operation. And then everything else is kind of self-explanatory, right? We have our min max size for the cluster and the warehouse size. As Hank kind of pointed to a little bit earlier, we have the max queue size, so we can decide if we want to scale in or out based on a custom number of queries in the queue, not just how Snowflake natively does it. We have this next flag that we use to determine whether or not we want to also have Snowflake natively scale the number of clusters, right? So if we set the cluster number to 3, generally, if Snowflake determines that there's not 3 clusters worth of work there, it would go down to 2, but it would still say that the cluster max is 3. For some workloads, we found that it's better for us and keeps the work more predictable if we peg that to min max of 3. So instead of letting Snowflake kind of do some custom scaling on its own scaling on the back end, for more predictable workloads, we want to make sure that Snowflake's not doing any scaling. We're fully in control of all that scaling that's being done. Then we have just a flag to see if the service is enabled or not, because we have this toggleable for all warehouses. So some warehouses might not be scaled at certain points in time or on certain priorities. And then finally, we have the kind of real secret sauce of this second iteration of the scaler, which is pegging these task latencies to the warehouse, right? So this particular warehouse, you can see at this point in time, is going to be using some more merge tasks as well as some more DAGs. And so these are execution times in seconds. So these are the SLAs we're trying to meet. And if we don't meet them, that's the scaling signal to scale up. And then just kind of a quick walkthrough of the actual kind of service in and out between Snowflake and the AWS Lambdas. So we have our get latencies function. So that's going to go straight to Snowflake, get the monitored tasks, find those runtimes, and report them back to our status Lambda. Then we're going to get our priority level. So we're going, like I said, I'll go into this in a few slides, but we're going to look at the game schedules. We're going to see, are we in an NFL game? Are we getting ready for the kickoff of another game? Is there any sports going on at all? What is our priority level? And what is the SLAs attached to that priority level? Now that we have our latencies and we have our priority level, we have all the information we need to know if we need to scale a warehouse up or if we need to scale it down. So we can check this, see that if that SLA has been breached. If it has, do we have headroom to scale up? If we don't have headroom, then we do nothing. We just log the event. If we do have headroom, go ahead and scale up. Same thing with scaling down. Is the task running so fast that we feel confident that we can do the next execution on a smaller size? Is there a smaller size available to us? Let's scale down. And then so with that kind of basic framework out of the way, there's a couple kind of conditions that we had to test and walk through and kind of try to find the edges for it, because it's not necessarily intuitive with this reactive approach, how to handle some of these scaling situations. So in a situation like this, we want to make sure that we're not preemptively scaling down when we don't know the accurate runtime per the job execution. So in a scenario like this, we have a job that runs on a medium. It comes in far below SLA, so at 40% of SLA, which for us would be a target for scaling down. But because we're only running the status check for the scaler every minute, this next job could be kicked off before we have the information, before we're able to scale. And then so now we have a job that kicks off on a medium, and with the way Snowflake's warehouse scaling works, is that even if we set it to a small right now, that job that got kicked off on a medium is still running on a medium. So if we were to scale down again, while that job that we thought was running on a small was running on a medium, we're not going to have an accurate indication of the execution time on that warehouse. So we need to make sure that we're looking at the last modified or the last altered date timestamp for that warehouse to make sure that once the job is the job that we are measuring against is accurately being run on the warehouse as we think it is. Because if it's not, then we don't want to use that measurement at all in our scaling prediction or our scaling decisioning. And we want to wait till the next execution to make sure that we are properly determined that we are at the right size. And so it's kind of the opposite for us when we think about scaling up. And then the fact that we don't want to lose executions or miss time if a job is missing SLA, and we want to make sure that the next execution doesn't miss SLA, right? So in this situation, we're perfectly happy with doing multiple scaling up in one job execution to make sure that the next new job execution is fully on a size capable of bringing us back within SLA, and we'll worry about scaling down and being a little bit more hesitant there later. But so in a situation like this, a job misses SLA, we kick off the next one on a side, kick off the next job, and on a size up, it's still missing SLA. So instead of waiting for another full run from a medium to a large and then a large to an extra large, we're gonna go straight to a 2XL because the miss on SLA there was large enough that we got multiple executions of the service in. And then we're gonna find that point where the warehouse is actually now running within our SLA time period. We're gonna get 2 executions where we're confident in meeting that SLA, and then we can worry about scaling down after. Yep, and then so a quick point on the kind of how we're determining our SLA priority periods. So for us, right, the business generally knows the sports and the time of the year and the time of day that are going to be our highest volume for traffic for users. So we want to make sure that we're scaling as aggressively as we need to for higher SLA times and higher priority sports for us. So we've put together a schedule of all of a dynamic table that pulls into the schedule for all the sports and all custom events, and assigns a priority to each of those based off kind of business need, business priority. And then this dynamic schedule then kind of bubbles up the highest level of priority at any point in time. So you can see like, on any day of the week, there's multiple sports going on at any point in time. If some are lower priority, we don't want those to affect the SLAs we need to hit for higher priority events. So in this case, NFL is king. So when we see NFL is a game is either about to kick off or is actively ongoing, those are usually going to be our highest priority events, which means tighter SLAs and more aggressive scaling policies for those time periods. But as soon as we leave those NFL time periods, we can immediately go into lower priority time periods for other sports without ever missing a beat and making sure that the highest priority SLA is always met. And this is just another view. This is within Snowflake dashboard, kind of the heat map of the different time periods on a given week of when we go from what we call a P0, which is kind of business as usual, a P1, which is probably low level sport priority, and then a P2, which is pretty much as aggressively as we'll scale for any point in time. Yep. And then, so this is kind of the last bit about building this out. One of the big things for the platform team was, before we had this auto-scaling service, a big issue for us was knowing when to scale and having all this scaling come through us and having to try and guess at game times or potential volume for certain events without ever knowing, if this is the correct amount to scale or if these are the correct times, or maybe there's a game in Europe this week that has a different time start time than we're usually used to. So putting kind of all this onus on the platform team to figure this out was never a good solution. It kind of led to some of the slides that Hank showed at the beginning. But now with this new kind of build out, we allow other teams in the organization to help inform that schedule, help inform that scaling, either through publishing what we call like white glove events, which are custom events where we want to have a particular level of scaling, or just tapping into other data that we have, such as the game schedules, so that we don't have to worry about it. It's automatically updated on the back end without us touching anything. Yep. And then so I'll kind of hand it back over to Hank for how that actually went.
So there's a lot of moving parts to this type of system, but it is still pretty simple. I'm sure people are probably interested at this point in figuring out, well, how does it perform? So I'll go over how we tested the scaling prior to the production rollout. I might, for the sake of time, sort of jump through the testing a little bit. I think it's probably more important to focus on the results. But the overall goal for us was to be able to replay the scaler on a period of time. So if we ran into inconsistencies or suboptimal behavior, we could debug, try out different policies, and rerun it. So the overall approach here was to essentially take all of the different tasks that we have, figure out what the sources were through like some lineage assessment, and then we wanted to clone all of these tables that we had from their source into a different destination. Now the different destination is like this sort of idea of a benchmark database. The benchmark database has different schemas per run. The runs are associated with a particular time period, and that's where we would essentially be able to start our replays. Now, one thing to note about these runs is that the slot has to be created within 24 hours of its start time. And the reason is, well, we have like the regular 24-hour look-back period for time travel. The reason that's important is because how long certain operations take on certain tables is dictated by the underlying partition layout. Different tables can have the same data laid out differently depending on your clustering, or really just depending on the time period it's in based on natural clustering of just inserting records. And so in order to be able to actually replay this, you can't just sort of clone the table now, delete newer data. You have to actually have the table cloned from that period in time so the partitions are the same. So the benchmark kind of looks like this. First, we clone the chosen slot schema of our benchmark into the run schema. We kick off a run, and this is essentially going to create a bunch of tasks that insert data into the stage tables of those run schemas each minute. That's going to simulate the data coming into Snowpipes. We do the inserting, so each task will check what the current time is on the run log state table. It's going to pull in the next minute of data from the live production table. It's going to insert that into the destination table. It's going to update the state. It's just like sort of running what minute are we at. And then once we've sort of completed the designated run length, let's say we want to run from this slot to the next hour, 2 hours, it's just going to automatically shut down the tasks and it's going to stop. So this is just a sort of very simple way for us to essentially replay our merge data in a very similar process, and that's going to help us sort of change some policies and iterate before we sort of deploy to production. So we just kind of covered the testing prior to development to deployment. Now we want to cover monitoring post-deployment. So we use Datadog for this. We have some runtime metrics coming in from our Snowflake tasks and our Airflow DAGs. One thing we tried to focus on was making it really easy to tell the overall stress of the system at a glance. So we use color coding of metric values based on the expected ranges at that point in time. So depending on what priority we are in, changes what our expectations are. And that changes how we care about the certain times that we're in, or the certain SLAs that we're getting. And so, as we discussed earlier, there's no perfect relationship between data volume and runtime, primarily because it varies based on the ratio of updates to inserts. Updates are much more expensive. You have to rewrite entire partitions, even for just one record. Inserts, much less expensive. So we can still see here that it's common for an increase in data to cause an increase in runtimes. If you look at that middle graph of the data volume, you'll see often there's a spike, and then you look down, and there's task runtimes that spike up. And then if you look up, we have those dark purple little squares. They indicate that we scaled up. And then the lighter purple ones indicate that we scaled down. So you can sort of see this is very similar to maybe what you would get with a data volume approach. And so here's an example of primetime game scaling. We can see that the scaling is a lot less periodic than what we saw before at baseline. And that's because we have a much higher sustained data volume. So what we just saw was kind of like middle of the day, things are just happening, little events pop through a bunch of data, but you get these big spikes because you're at like such a low baseline that the relative difference is pretty huge. But during games, we have much higher sustained volume. It's a lot of stuff happening just all the time. So you see sort of less changing of the scaling, but what we still need the service for is essentially to be able to scale down aggressively in order to not just be overscaled for the whole day. So diving into the runtime and latency graphs, we can see the dynamic color coding coming into play. So depending on which priority period we're currently in, that's going to change the SLA expectations, and that's going to change how we color code the bars differently. So it's not just like over under a threshold, it's over under what our expectations are based on the SLA period. We have the SLA period stored in a metric, and we can do some kind of clever sort of arithmetic in order to get these color codes to work based on the different priority period. So once we enter a non-baseline priority period, scaling kicks into gear. This is going to make sure that the execution runtime is where we need it to be. And then as soon as the games are over and we don't need low latency data anymore, the SLA relaxes considerably and it just scales like way. The SLAs run way much longer. So obviously, not everything went perfectly to plan. And so this was a really kind of fun thing that happened during the initial rollout. We were just sort of testing where we could push this thing to and how quickly it would recover and how responsive it was. So we just manually set the warehouse to 4XL, just to kind of see what would happen. The problem was, in order to make sure that the previous task runtime was for sure at the warehouse as we thought it was, like Tom showed in one of those graphs earlier, we only consider scaling down if the task started after the most recent warehouse alter time. Well, it turns out auto-suspend also changes the last warehouse altered time. And so because the jobs were running so quickly, they would finish fast enough that we would have over 60 seconds of nothing happening in the warehouse, because we don't normally run this at 4XL on this data volume. And so that means each time that we sort of have our batch going, it runs so quickly that the warehouse has enough time to auto-suspend. And so that was preventing it actually from considering that this job ran at this size. So it just stayed up at 4XL for like half an hour. We had to manually bring it down to planet Earth. So on theme with downscaling, this was a different approach that we took where we tried to essentially undo a downscale if we thought that we incorrectly scaled up scaled down. And so the short answer is this basically just sort of left our simplicity is king approach and started to get into like we have a number of different scenarios. And it just ended up muddying the waters with the base case scenario. And we found that this didn't really happen as often as we expected it to. And when it did, it wasn't nearly as bad as we thought it was. So we kind of scrapped that approach. So the one thing that we are looking forward to changing this on, even though it's as simple as we want and it's been working very swimmingly, is we think that if we added warehouse-specific priority periods, this would allow us to broaden the use case to other scenarios where this might be useful, but also to collect all the different scaling cases that we have. Sometimes we do just need a over-under during certain periods, and sometimes we want it to be more dynamic. Having it on one tool would be really helpful. And then finally, the big numbers at the end. For NFL kickoff 2024, we had 4 billion messages processed for that day. We had 768 scaling events, and those caused 0 SLA breaches and an only 15% increase in credits over baseline. Again, because we're not just scaling up to get those SLA breaches down, but we're scaling down aggressively in order to keep the costs from running up.